go to like the previous section, which was countability. What does it mean for a set to be uncountable? There's a non-satisfying answer and then a satisfying answer.
Just kind of listen about like break countable, like groups
Let's see, here's the countable sets section. So set X is called countable if either it's finite or it's in bijection with the naturals. So this is what it means to be countable. So just read the rest of that definition. What does it mean to be uncountable? It's just not countable. That's all. So there's the unsatisfying answer. If we want to prove that the real numbers are uncountable, so that's like not satisfying and not useful. So that's not enough. We need to keep on unraveling what countability means. And instead of using the definition, let's appeal to these conditions. Those conditions are all equivalent, right? So if we want to prove that the real numbers are not countable, we can prove that any of those conditions fit. So we can either prove that there is not a one-to-one function from the real numbers to the naturals. There would be one option. So I guess that would mean we consider absolutely any function from the real numbers to the naturals and then show that there have to exist two different inputs that go to the same output. That's what we would need to do. Because that's what not bijective means. Or we could show that there is not a surjective function from the natural numbers to the real numbers. That's the one we'll use, the surjective. So to prove not countable, we will show So now we've unpackaged some. We know exactly what we would want to show that the real numbers are uncountably big. We want to show that there's no onto function from the naturals to the reals. So that means that there's like no way to list the real numbers one at a time, even if you're allowed to repeat and be able to hit all of them. You'll always miss at least one real number, no matter how you try to list them. So there's our goal. Let's try to do it. And I want like you all to fill in a bunch of these things, not me. So there's the thing we want to prove. The real numbers are uncountable. We will do that by showing that there does not exist a surjective function from the natural numbers to the real numbers. Now, make a pass at explaining why. So corollary means it should be a result that follows from a theorem. So this should be really easy to prove if you assume that. So if you assume that you did know theorem 4.3.1, tell me why 4.3.2 should be true. Let's start with that. So, by theorem 4.3.1, there is no onto function from
n to r.
And now let's finish putting that into wads. Why does that tell us that the real numbers are not countable? Yeah.
Since every bijection is a surjection, there is no bijection from n to r.
And I don't see the word uncountable yet. So and I have some lines, so let's spill out all the logic.
By the definition of accountability, it must be a bijection.
Almost. So by the definition, I would say of cardinality. Certainly the size of n cannot be equal to the size of r, because if they were all equal, there would be a bijection. But if you go back to the definition of countability, there's a silly, dumb thing that's in the way of that just being enough. Countable means one of two things. It's either finite or in bijection with n. Yep. Yeah. Since r is not finite, and maybe right, there's an infinite subset. So, and you're all right, I've just get that, rearrange those ones, get the logic into something you like that all. So, if there's what we want to prove, this argument explains how to conclude that if you know theorem 4.3.1. So that means that the new goal is prove theorem 4.3.1. So, let's just unravel that statement. So we want to show we want to show there is not a surjection from n to r. But that's too negative a statement. Instead of showing there is not a surjection, let's show for every function, that function is not a surjection. Do you agree that's the same? So let's just keep unpackaging. Unpack. Every f from n to r is not onto. What does it mean to not be onto? Well, what does it mean to be onto? What's a surjection? Yeah, everything in the codomain is hit. I don't like saying every output is hit because output already sounds like a thing that's hit. So everything, it is not the case then that everything in the codomain is hit. That's again too negative. Let's unpackage that. So that's the same thing as for every f from n to r, it is not the case that every x in R is
hit. So let's unpackage that not statement so it seems less negative.
So there exists some X and R that is
Nice. Cool. So we want to show that for every f from n to r, there exists a real number. That real number should probably be x, such that x is not hit by f. Groovy. So we know what we want to show now. And, well, we already have a separate name for something that is a function from the natural numbers to the real numbers. What's the word we have for that? A rule that associates a natural number to a real number. Well, that's a sequence, right? Yeah, that's all. So we want to show that every sequence fails to hit something. And to do that, here is the lemma that we will use. And you know what? I'm going to pause for a moment. I want to put on the board the statement of the nested intervals theorem. Do you remember what the nested intervals theorem says? You have your notes on you though, right? Or just do you remember?
Is it like if I and n plus 1 is a subset of I and n, I don't know, there's just some element of, I don't know, isn't all of i's there?
Yeah, so if, I'm going to add like a little clause here, if I is a sequence of closed bounded intervals. And the thing you said, then there's something in the infinite intersection. So that's the nested intervals theorem. We'll use that. And you know what, I think that's the right statement, but like, open up to like where it is in the notes, and probably the wording's a little different, but convince yourself that it means the same. Oh, and like, that numbering tells you how to find it too, right? It's in chapter 3, section 5, and then it's the Faust theorem in there. Nice. So, this gives us a strategy. The strategy is going to be, let's find a sequence of intervals which like tries to zoom in on a candidate value that's not going to be in the image of the sequence. So, the bulk of the work is going to be filling in the details of this lemma. So let's let xn be any sequence. Then, and you'll prove this by the end of today, there is a sequence of nested closed bounded intervals, like those, satisfying that for every natural number n, the nth term of the sequence is not in the nth term of the sequence of intervals. So, like, that also seems intuitively true, right? There's x1. Here's I1. That doesn't contain x1. Maybe there's x2. could you find a smaller interval that misses x2? Yeah, right, and like, making it precise will be like some f odd, but like, that'll do. There's x3. Could you find an even smaller interval than I2 that does not contain x3? In fact, could you just use I2 again? Cool. There's an intuitive proof, but it's not like the proof. So here's what I'd like you to do now. Go through this argument. So assume lemma 4.3.3, and then prove theorem 4.3.1. So if you want to prove 4.3.1, you want to show that there does not exist a surjection, so let's consider any function. If you can show that function is not a surjection, then you've just shown that every function isn't a surjection, so there is none. So we need to find a real number not in the image of f. Xn equal to f of n defines a sequence. Use lemma 4.3.3 and go from there. So I'll let you like talk amongst each other. I want like 5 or 10 minutes, and I'll pace around. So that means you satisfy the assumptions of lemma. So that because you assume the lemma is true, that means you know that the conclusion of the lemma is true. So by lemma 4.3.3, you just know everything after this event is true. Everything So let's like talk through the idea. Excuse me. Excuse me. So let's talk through the argument here. So you start with, you want to show there does not exist a surjection. So you consider any function f. You need to show that function is not surjective. So you need to show there's something it doesn't hit. And we've got this like intervals lemma that we can appeal to. So let's let xn be defined by f of n. That gives us a sequence. So what does that lemma let us conclude? Since we have a sequence, what can we construct? Yeah, you just did too much though. Like, just what does the lemma let us do?
Does it let us say that like xn isn't in the intersection?
It will, but the intersection of what?
Oh, of course not intervals.
Yeah, but like, where are you getting them? So all I want you to do in this line is, it just says by lemma 4.3. So let's just ask ourselves, do we right now satisfy all of the assumptions of lemma 4.3.3? Do we have a sequence? That's all we need. Since we know the assumptions of the lemma are true and we believe the lemma, we know the conclusion is true. So all I want in this line is the conclusion of the lemma is true. So, by lemma 4.3.3, we see that there is a sequence of closed, nested, bounded intervals in such that for all n in n, xn is not in in. So I've just copied down, I think even verbatim, the conclusion of the lemma. So whenever anyone says like, by result such and such, this happens, they better just be using that result. If they're using that result and some other stuff, then it better not be much other stuff. Now let's say what you wanted to say. Next, apply the nested intervals theorem. So what does the nested intervals theorem let you conclude? That the infinite intersection of a lot of them isn't empty. So I guess there's the actual statement that's in the notes. But there's a thing in there is the same as is not empty. So you can apply the nested intervals theorem to allow you to conclude that the infinite intersection of the INs is not empty. Cool. If it's not empty, then there's something in it. Maybe you called it X, maybe you called it Z, whatever, I don't care. The next prompt is explain why f of n cannot be equal to z for any natural number n. Why is that? Emma, some of the stuff I saw with it looked pretty okay. So.
Because he is an IN and X of n is
Yeah, z's in the infinite intersection, so it's in every one. So z has to be in in. Is f of n in in? No, by like the thing we got out of the lemma. Oh, if one of them's in a set and the other one's not in a set, they can't be the same. That feel pretty good? Nice. Oh, by the way, this is a group walk item, right? So I want to collect your write-ups to this as the homework for today. Just pointing that out. All right, so, cool. So what was the logic so far? If there does not exist a surjective function from the naturals to the wheels, then the wheels cannot be countable. If this lemma is true, then there does not exist a surjection from the naturals to the wheels. But we know that that means the wheels are uncountable. If we can prove that lemma, then we win. That feel pretty good? Groovy. So we just need to prove that lemma. And this next bit, I think, is the last bit that I want to say before I just cut you loose to prove the thing. So let's do some scratch work for that lemma. So the lemma says let xn be a sequence. Then there is a sequence in of whatever intervals such that some stuff happens. A really good way to show that something exists is by building it. If you could literally construct this thing and say, here it is, then it definitely exists. That's not the only way to prove that something exists. There are some like really wonky proofs that are like totally non-constructive that a thing exists. So let's try to prove this by like coming up with an example. And in order to construct a sequence of intervals, let's just start building them. So, scratch walk. Start with a sequence. We'll come up with a recursive definition for in, but whatever. Let's start with the first step. I need x1 to not be in I1, and I1 to be a closed bounded interval. So on that like number line down there, draw an example of a closed bounded interval that does not contain that point x1. I just want to like come up with an example. So like drawing fiction will be a good place to start. And now like label the endpoints in some way that's like many choices. What seems like a good choice for A1? X1 plus or minus something. And I guess whether you do plus or minus affects your choice of B1. So, many options. Let's hear someone's. What does someone want I1 to be? Yeah, it will definitely depend on X.
Could you do x1 minus 2x1 and then x1 minus x1?
I think something might go wrong if x1 is 0. So I think go easier than that. Okay, I think they're looking for something that's fancier than you. Yeah, cool. So it looks like you just need like 2 numbers less than x1. How do you come up with 2 numbers less than x1? Yeah, it is. Okay, you just wanted what's the symbol next to x1? Oh, cool. What about alpha and beta? Yeah, I guess they even better be positive. Well, they should be correct. Yeah. No. You have too much freedom right now.
So could we just do like x1 plus 1 and then x1 plus 2?
I think that will walk. Is that a big closed bounded interval? Does it exclude x1? Yeah, so just be as explicit as possible, as simple as possible, ideally. So one candidate I had was x1 plus 1 to x1 plus 2. Did anyone come up with different candidates?
Can you switch them and just use your direction?
Sure. What endpoints do you want? That'll work. Anyone come up with other things? Those are two intervals that definitely don't contain x1, right? Nice. I guess the difference is whether or not you want the picture to look like that or like this. Both fine choices. All right, so I said we're going to do something recursive. So there's a starting point. There's like the base case of the recursion. Let's try to figure out how to find I2. So what do I need I2 to do? I need it to be a subset of I1, and I need it to not contain x2. So let's see what we can do. So if x2 is over there, and there the stuff that's bolded is supposed to be I1, well, it seems like a good choice for I2. So what do I need? I need I2 to be a subset of I1. Yeah.
Would we be able to do A1, B1?
Yeah, let's check it. Is x2, if you assume that picture, definitely not in that interval? Is that interval a subset of I1? Yeah, and that's why it's really nice that like there's the line underneath the subset symbol to allow you to be equal. You don't have to make it strictly small. All right, so let's go on from there. Let's suppose that x2 is like strictly in between a1 and b1. Can you come up with a subset of that which does not contain x1? I suggest starting by drawing a picture. And then figuring out some numbers that'll make a block. I saw some reasonably compelling pictures. And most of them were some variation on this theme. So, what things do I need A2 and B2 to do, and then we'll try to like come up with explicit choices. So what do I need A2 to do? For this picture to be like correct. Needs to be bigger than A1. And I think bigger than x2 would be good too. Because then I would know that I miss x2. What do I need B2 to do?
Be less than B1.
Be less than B1. In fact, less than or equal to would be good too. In fact, can we just take it to be equal to? Would that be okay? Oh, cool. So I guess let's shade in more of this. And I guess that means that A1 had better also be less than B1. A2 had better be less than B2. So, I think that's a good choice. So it looks like I need A1 to be something that lives in between x2 and B1. What's a way of building something that's in between two numbers?
Take the distance and divide by 3.
Yeah.
The lowest one?
That'll do. Let's simplify that then. So let's just go off to the side. So you said start at the left one. So A2 will take it to be x2 plus the distance from x2 to B1. So that's B1 minus x2. Oh, that should be a 2. Divide by 2. Like that? Yeah, so now let's simplify that. I don't want to do it, but you do it. Because like it your intuition's good, but like that looks complicated.
Can we just get rid of the plus x2? We just use the midpoint. Might be a little bit simpler afterwards.
B1 minus x2 over 2. I think the trouble is that I need it to be bigger than x2 as well. Yeah, and this is the average, isn't it? Yeah, yes, that's what I was trying to get you to say. That's the formula for the average. If you want something that's between two numbers, try the average. And that's just like generally true. If you just want something that's between two things, take the average. As long as you don't care about anything else, which I think we don't right now. So let's do the average. All right, that's 2x2 minus x2, so that's x2 plus b1 over 2. All right. The only time that will be bad is what if x2 is literally equal to b2? Like then, like the average between two things is a point, and we'll be down to a single point. Well, that's bad. Intervals are not equal to single points. So, separate case. If x2 is literally equal to b1, then what's a subinterval of that misses x2? Let's do the opposite. So what will A2 be then? Like that? What will B2 be? Cool. That feel all right? So, it looks like our definition for I2 is like a case-wise thing. If x2 is not in I1, let's just use A2 equal to A1, B2 equal to B1. If x2 is in I2 but it's not equal to B1, then A2 was the average. B2 was B1. If x2 is equal to b1, then a2 is literally equal to a1, and b2 is equal to the average. Cool. That feel pretty all right? Is that the only choice of interval that we could possibly have found? No, there are obviously tons of others, but I think that's a reasonably simple one. And we don't need to like completely classify all sequences of intervals that do the thing. We just need an example. So I think we have the choice for I2. In fact, do you think we could do a similar thing to go from in to in plus 1? Yeah, I bet. Maybe it's awkward there's like a page break here, because maybe you want to copy down what was on the previous one to get what's on the next line. So maybe I'll flip back. So, try to see if we can use the same ideas. But I do want both. I can have both. I can do both. I have enough time to do this bit of shtick. There we go. So, yeah, this'll do. Yeah.
You think those you probably have to do with ends instead of 2s and 1s? Yeah, okay, so fix that. And I guess you have to fix that down here too.
So, let's see. Well, I guess that means that I want to actually write it. If xn plus 1 is not in In, then what do you want an plus 1 and bn plus 1 to be?
A1 plus 1 equals
That seems reasonable. bn plus 1? Nice. And the same thing, x n plus 1 is in an, but it's not equal to bn. Then what would you want an plus 1 and bn plus 1 to be?
an plus 1 being xn plus 1 plus bn. Plus bn.
Yeah. And bn plus 1? That's certainly consistent with what's on the previous page. And the last case, if xn plus 1 is equal to bn, then what seems like a reasonable choice?
An plus 1 equals bn.
Cool. bn plus 1?
The average of bn.
Groovy. All right. So there's like a sketch which I think is pretty convincing. Now it's just a matter of checking some details, which will like take some writing, but it won't be bad. So here's what I will have you do, and this is essentially the homework now. So let's let xn be a sequence. We need to find a sequence of nested closed intervals, blah 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 blah. Let's define A1 and B1 to be exactly the thing that you found seemed reasonable on the previous page. Let's define AN plus 1 and BN plus 1 to be the thing that you just saw was reasonable above. You now need to show that for every natural number n, IN plus 1 is a subset of IN. Does that seem like it probably won't be so bad? I think there's going to be like a case-wise argument, because there are like 3 cases for what xn plus 1 might be, and the 3 cases affect what IN plus 1 is. But like, in each case, is that interval clearly a subset of IN? In fact, is it the same interval as IN? Is that interval fairly clearly a subset of IN? Yeah, maybe you have to muck around with some inequalities, but it won't be that bad. Is that interval fairly obviously a subset of IN? Yeah, you'll need to muck around with some inequalities, but you can do that. You also need to prove that xn is not in IN for every natural number n. So I guess the weird case will be n equals 1. But like n equals 1 was set up to be obvious, right? If our choice of A1 and B1 is good. Then you need to show that for every natural number n bigger than 1, and let's see, something that's bigger than 1 is something plus 1. So, use that. Cool. Do you think you could complete this proof in maybe, I don't know, half hour, an hour's time? Do you think you can complete this proof in some amount of time? Okay. There's the main thing. Once you have it written, like, every step will be, like, for each step, write down what you want to prove. And then prove it. And it'll be like a bunch of set containments. You know how to prove set containment, especially since these are just intervals. You want to prove xn is not in In. You need to prove that some inequalities don't happen. Just prove that those inequalities don't happen. So there will be like 6 steps or something, but I think each step will be easy. At least that's my goal. And I'm well past time. Yeah.
We will have to show
Yeah, that should be x 10 plus 1. Yeah, that's it.
And then in our case, it should be the same.
Monday, Wednesday, Friday, that 4 classes.
Okay. Cool.
Yeah, and then with the practice that.
Any plans for the weekend?
I seem to have plenty of homework that